All right. Well, it's a privilege to have the opportunity to share some highlights from the Andes Lidar Observatory shown here on Cerro Pachon at roughly 30 degrees south in Chile at around 8,200 feet elevation on one of the astronomy facilities, which I'll show shortly. Fabio Vargas, my colleague and site manager, has taken this exposure around the southern pole. As you can see, the stars rotating, gorgeous star field, I should say, at the site, with three beams going out into the zenith and south and east to do winds. The facility, we packed the facility in, from Urbana in a shipping container in 2009, showed up in September and unloaded the boxes. Notice Dave said yesterday started the deep wave campaign politicking about that time. And it takes a long time to develop these facilities, and this indeed is an observatory. It's not just a LiDAR, it's imagers and a consortium of people interested to explore the dynamics and chemistry of the upper mesosphere, lower thermosphere. At 30 degrees south, we're right on the border of when the diurnal tide and the semi-diurnal tide dominate this site. And as we take winds during the night or temperatures, what we'll notice is one or the other dominates. And for the students, how do we tell that? Well, in the perspective of observations of temperature, the semi-diurnal tide has a vertical wavelength of about 50 kilometers over a 12-hour period. So the phase progression in time is about 4 kilometers an hour, steep gradient. Diurnal tide, on the other hand, has a vertical wavelength of about 20 kilometers over 24 hours, and a phase progression in time of about a kilometer per hour. So there's a steep gradient change of the dominance or one or the other. So as I talk about data, we'll just talk about what kind of a tide night it is. Because what happens is, I'm going to show data where we have a lot of coupling going on between what we call wave coupling, wave-tide coupling, and indeed the tides set up a dynamic and a thermal condition to which waves coming from below couple with. I'm going to talk about a little bit more about where it is, the people. There's a large number of people involved in working the facility, providing the instrumentation. And we have a new performance LiDAR that's been upgraded with a new transmitter with MRI from NSF, as well as sensor technology to put a jump of almost an order of magnitude in sensitivity. And we're very excited to show some of the results contributing to large wave, small scale insights that are just now begun. We're here at 30 south, I should say, just at the Appleton anomaly, which Bella nicely introduced. We're sitting right at 18 degrees south magnetic. So Jonathan Makela has a camera on Tololo, adjacent to our mountain, that's looking towards the equator to do red line and also TEC measurements. And we're located on Pachon, along with two large telescopes, Gemini and SOAR. And I should say the SOAR telescope is 4 meters. In the big picture of things, the SOAR telescope has a Hawaii detector at infrared wavelengths, to which we're working with to make a first light helium experiment later. But we're very cooperative with this group. They're in the process of putting the LSST telescope on the mountain, on the hill just around the corner from the Gemini over here. They're already cutting dirt and have a lot of people up on the mountain starting to build that facility to come online in about 3 years. In fact, we have 2 people two groups from the astronomy community now with instrumentation studying and preparing for the LSST. Here's a bigger perspective. Here's ALO next to the cafeteria and dormitory. We don't have line of sight directly to these observatories for the reasons that they did not want to see our lights or interfere with anything they do, understood, but they're most willing to share their mountain with us. The Gemini uses 589 sodium as a guide star. They actively move their telescope and distort for focusing their telescope with that technology. And of course, a big part of their welcome for us on the mountain is that we study the sodium layer, which contributes to their understanding of the target they have for guide star. So we often have coordinated interests to operate at the same time. Here's ALO. We actually worked with the University of Illinois to get $100K to build the building, and as gift money. And this points north. North is to the right in the picture here. We have a transmitter room, receiver room with 4 active mirrors, 3 of which we're using currently. And then the passive air glow rooms on the right with a furnace room in the middle. Aerospace Corporation is located here with a temperature mapper. Infrared camera, I should say, Jim Hecht. And they're about to put in a 2K by 2K infrared camera with, into this room with, in the next few months. And we're very excited to see that. That'll add another new dimension of spatial imaging to the site. Then we have all sky cameras in the right here, right side. And here's a little bit more attention to credits on instruments. We're working the Lidar along with Alan Liu, our lead scientist for ALO. He's at ERAU, and his students are responsible for a lot of the data I'm about to show and signal processing, as well as Fabio, who's the site manager. Tony's a grad student, just graduated off at MIT Lincoln Labs now. And of course, Chet's in the audience, our early founder, along with Joe Shea. We're indebted to those two explorers in this business. Alan and Fabio operate the all-sky camera. We have meter radar, infrared imager I referred to from Aerospace Corporation, and Mike Taylor runs a OH temperature mapper along with Dominique and Yu Cheng. And then Tony developed the 3-channel photometer in the Zenith, and Fabio and he have operated that. I should say that we're at a site and we're part of CTC, or the consortium of LIDARs that Jeff Thayer manages the group, along with the CTC at University of Colorado's Inzhao Chu. I'm going to refer later to some of the upgrades, much of which came out of Inzhao's group for our system. 2 other systems, Titus and Mike Taylor run the USU system, and Dave Fritz and Biff Williams have the Alamar LiDAR. So part of the business that we have is it's a cooperative one where we're communicating to each other about technologies and have a central core group that manages attention to upgrades and technologies and so on. And this is an important exchange process where we're not holding things in ourselves, but share data and coordinate activities. That's an important aspect of the way we work in the NSF and CEDAR community. We're also indebted to Aura, of course. We're renting the turf from the astronomers, and they have 20 people a day coming up to work on telescopes, technologists and engineers, and as we need some support, they're there for us to ask for support. And they'll fix things for us. They'll send us a bill, of course, but they're there, and that's an important aspect of this. We pay about $40K a year for the rent, utilities, road use, ambulance person sitting on the mountain, all those things. But it's a gorgeous facility, well run. I should add to the people we're indebted to Rich and Bob, of course, who started this. Thank you. We wouldn't do this, of course, without the support that we've had from NSF. This is Lidar Receiver. Here, this shows Alan and I think that's Tony back there. They're adjusting things. This is the receiver. Right now we're using 3 telescopes, zenith, south, and east for winds. And as the system was upgraded a year ago, from now the receivers were also upgraded with new fibers. And the combination of the transmitter upgrades and the receivers have given us this nearly a factor of 10 in sensitivity. John Smith and Zinzao, John Smith was, and is Zinzao's grad student, was a major contributor to this. Yes, as a grad student, you can make a big difference, and John did. Thank you. He's not here today. This is the new system. We put a Toptica CW solid-state laser in here, replaced a pump to an old dye laser system that was very challenging to operate and relatively unstable compared to this. With this new replacement, we now run the system with a single person, not 2 or 3. That's a big change for us. This is a very stable laser. It locks in. We run it through a sodium vapor cell to have a frequency lock. This puts out a CW beam to 3 frequencies through an acousto-optic system. This has been there since the early days, and still the way we run the CEDAR into a dye amplifier, which is pumped by a large power YAG laser. Out goes the pulse, about 1.5 watts, 1.5 to 2 watts. So indeed, you need, I want to just remind everyone, you need 10 to the 5th photons back to get precisions of about 1 degree or 1 meter per second in wind. And now we're just doing that much more quickly. We've had 49 days of data for at the high resolution mode in the past since last year. Last year we ran zenith only with upgrades that had only been in the zenith telescope, and in January put in the upgrades in the receiver for the horizontal winds. And so in the last 3 campaigns we've been running with new winds mode as well. We plan a campaign starting in a few weeks. Fabio's going down to run one in July. Then we plan another one in November, October timeframe. And I should say that later we're planning a major campaign in next summer, along with the new imagers that we're expecting aerospace to put in, and encourage people to think about how you might contribute to want to participate in that. So this is before the upgrade. Just shows you the resolution we have with binning 1 kilometer or 0.5 kilometer in 90 seconds in time, approximately, in zonal and meridional sodium density and temperature. And this is the new machine. Of course, you can see in that same integration time, temperature, density, meridional wind I'm showing here on the right. By the way, shows that we have this, looks like semi-diurnal tide in the slope, but a very large amplitude here. That's minus 100 meters per second. And this is positive over a range of about 6, 7, 8 kilometers. So the shears are huge in this part of the wind field. This is vertical wind now. I'm just showing this on the right. And see if let me go back to that. I thought I had some blown up pictures of this, but vertical wind, you see this hotspot originating. By the way, you can see the densities being kind of pulled up and torn into a large overturning shear or instability kind of thing. And you can see the vertical winds here. There's upwelling trend here, but large downwelling just at the top side of the shear. And that kind of in excess of 10 meters per second and almost 100K hot spot here was unusual, and we're studying this fact that it might be something to study in detail with the instability models. But this is the type of data that is going to be very exciting to study. A new phenomena that's also been discovered is as we bin data in larger bins of a few kilometers in altitude and longer in time, we're seeing these sodium plumes evolve and go upward into the E region. We have, out of 47 nights, we have something like 18 nights, if I recall, where we see these plumes. I call them tidal plumes. This is one we caught, and I should say it's the only one that has a solid 8-hour period, or what looks like to us is the terdiurnal tide. And it has a phase progression that corresponds to about an 80-kilometer vertical wavelength, which is what the modelers contend would be the terdiurnal tide. I've taken this from Duo and Ward simply because they had a very convenient study that showed this is the allo latitude, and in temperature, zonal, and meridional wind. And it just shows what the perspective is, that this tide doesn't appear until you get above 100 kilometers, and they pulled it out of the study with the ECAM, or Canadian model. And in that paper, the discussion is around the same vertical wavelengths that we're seeing in this particular event. But in the other 17, 18 nights, we have plumes like this that don't show, they'll show a single event coming off, always usually at the same time, tidal-like. In this case, you look down, this is from 80 to 170 kilometers. The lower panel shows the high resolution data we have in temperature for that same night between 80 and 105 kilometers. And you see the presence of the semi-diurnal tide here is a major phenomenon, or dynamic influence. So as we've done a spectrum on that terdiurnal tide night, in the data from 90 in that lower altitude region, there clearly is a terdiurnal tidal component, as well as waiting on the semi-diurnal tide. So it's certainly, the data is of sufficient quality to show that indeed that's the period we're seeing. I'm going to show a few more. These are 3 consecutive nights. Alan's had a lot more data yesterday in the campaign. And in fact, in these nights, it looks like it's semi-diurnal tide nights down in the mesopause region. And we have this bulging like plume that goes up into 130, 50 kilometers, at 170 at times. And it's a persistent feature in the fall. In the summer, in January, we don't see any. If I look at the spectrum of this one, we indeed see more of a semi-diurnal tidal signature. In this one, we also see kind of a 4-hour wave coming in, which shows up in the spectrum. So there's studies going on between ALLO and Australia showing the 2-day wave that are in synchronous for the meridional winds. This suggests it's locked or forced by the n=3 wave. It's synchronous. The 2 stations are 60 degrees apart. And just show a few slides from small-scale waves. As we look at phase progression and filter the LiDAR data for these small-scale waves, we can filter them for the same period we see in air glow and get the vertical wavelength and amplitude and so on. Here's one day where we've done that, where we filter the data, and we look at the photometer data and phase progression, and indeed through the photometer data now we also can get the similar vertical wavelength from the data. We've done studies with the ripples and the instabilities, showing secondary instabilities originating from ripples and shape structure that evolve from both convective and dynamic instabilities that are pretty well understood and described by classical models from Peltier and Fritz. And lastly, I'm going to just show we've got a number of nights with waves penetrating up, but get blocked by these thermal inversions. Not unexpected, because the temperature in these regions are changing slope in highly unstable regions. Waves penetrate to those altitudes. This is the kind of resolution that's being done by the Alan and his graduate students to understand that these waves are showing up, and then they're evanescent, like going through an instability region and showing up as again above that as energy leaks through, and then going off in a propagation direction as well. So these are being measured and now simulated by Jonathan Snively and the Embry-Riddle group. They fit also, this is the imaging data that matches the vertical velocities with those waves. They're also on the next night, they're bumping up against these inversion layers. The last night, they're going up. This is a very steep night, and the waves are penetrating all the way up to 105 kilometers until they're blocked by the inversions that are set up. So this is a lot of wave-tide coupling going on. So in summary, the ALLO is an observatory well equipped to perform geophysical measurements. We're very excited with the evolution into the next phase now that we have. And lastly, say sayonara to Tony, who's gotten his PhD and made tremendous contributions to ALLO and is now off at Lincoln Labs. We hope he comes back to the CEDAR community in another day. Thank you.